Hello everybody. We are still talking about the mass transfer between phases and the graphical representation of the equations, and we have been talking about the how we can draw straight lines in or using the point and slope. And there is one more information or piece of information that is important, and we will need it while doing the graphical representation. And I'm gonna it's very related to what we did before, and I'm gonna cover it very quickly before we go through the graphical representation of the equations that we derived before. This point is about the solution of two equations simultaneously. So let's say we have two equations, equation 1 and equation 2. These two equations, this is a linear equation, this is a polynomial second order equation. It can be polynomial or any other equation, but let's say we have these two equations together here and we want to solve them. What I mean by solving these two equations simultaneously is to get the values of x and y that satisfy the two equations. So what I mean that I have a value of x that I plug in this equation and produces a y, which I know as well. So I know x and y, so I put the value of x, so solving this equation will give me the value of y that I have, and plugging the same value of x here and here in this equation will produce the same value of y. So this is a common point between the two equations. So the way we solve them, which is the easiest way or the most logical way of solving this, is by solving this mathematically simultaneously by putting these two equations equal to each other. So I say a1x plus b1 equals a2x squared plus b2x plus c, which is this, and then this is second order polynomial equation, and it's one equation and one variable, so I can solve it with any means. I can solve it by simplifying it and using the formula, or by simplifying it into two brackets, or by even iterative solution. There is a mathematical way that I can use to solve this equation because it's one equation in one unknown. So I can calculate x, and from any one of these two equations, and I can calculate y, and then I have everything solved. But there is another way that I can do it, and as we said, that the point x, y is a common point between the two equations. There is another way that we can use to solve these two equations simultaneously, which is the graphical way. The graphical way is simply by converting each one of these, or representing these two equations in the form of a graph, or a line on a graph. So this is, let's say this is a relation between y and x. So I have y and y axis, x on x axis, and I will plot the two equations. So the first equation is a straight line, which is equation number 1, and equation 2 is a second order polynomial equation, so it's gonna be a curve as we see here, and simply the answer is this point. This is the graphical solution, and as we did here, we were able to get a point or a value of x and y that satisfy the two equations, which is a common point between the two equations, which is a common point between the two lines that we see here. So this is what we or how we can do the graphical solution of two equations, is to get the point of intersection of these 2 points. So this is what we're gonna be doing in the graphical solution. Of course, this method is not gonna produce accurate results as we have here, but we tend to use this method if we have one of these two equations available in the form of tabulated data. Sometimes you don't have the two relations that you have in form of equations. This is one form of representing the relation between x and y. Sometimes you have the relation between x and y in form of tabulated data. So in this case, it's easier for you to draw the tabulated data and plot the other line, get the intersection, or the other option is to do data fitting to get the equation that fits with the tabulated data, and then use this equation with the other equation to get the solution. But this is might not be an easy way to do it compared to drawing the two lines. So this is what we need to know about the graphical solution of two equations. So now let's go back to the flux equation. This is the equation that we got from the flux balance when we said that the flux or we did the balance on the interface, we said that the flux going into the interface equals the flux going out of the interface, and we represented the equation or rearranged the equation to be in the form of difference between 2 points, delta y over delta x equals slope. So if we have a graph where we have y-axis is the partial pressure, which is the numerator here, and concentration is on x-axis, which is the denominator here, and then if we want to represent this, so it's gonna be a straight line that connects 2 points, PA and CAL, PA interface, CA interface, and the slope is negative KL of kg over kg. This is what we should expect from this line. We have already the equilibrium data. This is, as we said before, this is a must. I must know the equilibrium relation for the system I have, and we talked about this a lot, and that's why this should be the first step ever, is to have this equilibrium relation plotted or tabulated, and then you plot it based on the information that you have. And once you have this equation, you're done with representing the equilibrium data, which is this line. I'm sorry. And now we said that this left hand side or the straight line will be represented by 2 points. The first point is PA and CAL. In a case like this, we have low partial or high partial pressure and low concentration. So I have low concentration here. I have high partial pressure here. So this is the first point, PA CAL. The other point is PA interface, CA interface. And we know that these 2 points which are these 2 points? According to the two-film theory, these 2 points are in equilibrium. We said that there is no resistance at the interface, so these 2 points are in equilibrium, which means that they satisfy this equilibrium equation as well. So the second point is a point on the mole balance line and on the equilibrium line as well. So it's a common point between the two equations. So that's why the interfacial concentration and pressure will lie here on this curve, and then when we draw the line, its slope is gonna be negative KL over kg. So this is how we represent it. Of course, this is the final form of the graph. This is how it looks like at the end. But when we do the solution ourselves, we'll see that there are some missing information that we don't know, and we will use this graph to get primarily the interfacial concentration and pressure. This is the main or the first output that we get out of this. But before we go through the calculations and how what information we know and what we don't know, and how we can go through the solution, I would like to take a few minutes to talk about the significance of this graphical solution or the graphical representation of the equations, because it tells a lot about the system, more than what you know from the equations. For instance, here you can see clearly that this is the equilibrium relation, and this is the operating point, or the first point where this is the relation between the bulk of gas and bulk of liquid. So you can easily tell here by just looking at the point and the equilibrium curve how far you are from the equilibrium. It's not something you can tell by looking at the equations. Let's say I give you two equations or one equation, which is the equilibrium relation, and I tell you that I have the bulk concentration in the liquid and gas phases are these points. You can by no means tell that this, even if this is an equilibrium relation, you cannot tell without doing calculations. Here you don't need to do anything. You just look at the point, you just put the equilibrium relation, put your point, and then you're done. You know how far you are from equilibrium. Is it gonna be like a lot of driving force, small driving force? This is something you can easily tell. Also, regarding the driving force, you can easily see the driving force. In the gas phase, the driving force is PA minus PA interface. In the liquid phase, the driving force is CA interface minus CL. So this is something you can easily see. The CA minus CAI minus CL, it's this distance. So this, you can see the driving force. You can see it visually with your eyes that this is the driving force. The same for the gas phase. This is PA minus PA interface. This is the driving force. So you can easily see the driving force. We will talk later about more details that you can know from the graph regarding the overall driving force, regarding the contribution of each of the phases to the resistance in the system. There are more things that you can get out of this, but for the time being, let's just stick to this information that you can know the driving force and how far you are from the equilibrium in the system. This is also valid for any other unit system. So let's say, or what we saw here was the relation in terms of pressure and concentration, or partial pressure and concentration. But if you have, or you represent your system with the units of mole fractions, for instance, then you can do the same, because again, this is a graphical representation to the equations that we have in the system. So if I have the equations represented in the form that is put in terms of mole fractions, so I have here mole fractions in the bulk and then mole fractions in the interface, and this is negative kx over ky. It's exactly the same arguments that we did before and the same procedure, and it's gonna give the same output. But the difference is that you put the axes in the units that fit with the equation. So here I have it as mole fraction in the gas phase, which is the numerator, the mole fraction in the liquid phase, which is the denominator. The slope is negative kx over ky, and still I can get the interfacial concentrations. I can, or mole fractions, I can tell the slope, I can see the driving force, I can see everything. So this is very, very nice thing. You put your equations and then you translate them into lines on the graph. So regarding the difference in the units, there is something that is important that we need to discuss, which is the forms of the equations. This is something that we mentioned in the very beginning of the convection part of the course, when we said that there are many ways of representing the mass transfer coefficients based on the driving force, or the units of the driving force. So this is also something that we need to revisit here. So here we have the liquid film, and this is important to keep in mind that we are talking about two different phases. So we have the liquid film, we have the gas film. In case of liquid film, we can represent the flux in the gas film using two different methods. You can represent it using the driving force of molar concentration, so this is gram mole per centimeter cube, and in this case we multiply it by KL, and KL is the mass transfer coefficients in the unit of centimeter per second, and you have to make sure that the multiplication of these two is going to give you units of moles per area per time. So this is kilomole per meter square hour, mole per centimeter square second, whatever. So this mass transfer coefficient fits with this, so that they both give the desired units of the flux. The same liquid phase, for the same liquid phase, can be represented, or the flux in the same liquid phase can be represented using the mole fractions as the driving force, and in this case it's kx multiplied by x interface minus x in the bulk. So this is the same as this. It's only a matter of representing the driving force. These two equations represent the same system. So there should be some relation between these two mass transfer coefficients, because there is a relation between the concentration and mole fraction. So for the liquid film, if you are discussing it, then you know that this is the flux using the concentration driving force. And if you represent the concentration or the flux using the mole fractions, we know that mole fraction is the concentration divided by the total molar liquid concentration, which is the total number of moles per unit volume. So I can represent X interface and XA as C interface over CL minus C over CL. CL is the same in both, so I can take it as a common factor here. So I have the equation is Kx divided by CL multiplied by CL interface minus CA. This is exactly the same as this, because it's the same system. So here I can say that KL equals Kx divided by CL. So there is a relation between the mass transfer coefficient with the units of concentration and mass transfer coefficient with the units of mole fraction. The same is valid for the gas film. For the gas phase, I have the driving force can be represented in terms of partial pressure, so it's P minus P interface. In case it can be represented as mole fraction, which is Y minus Y interface. It can be represented as a molar concentration, which is C minus C interface. So these are different forms of representing the mass transfer flux, and then the mass transfer coefficient will vary to make sure, or to fit with the driving force. So here it's kg, will have the units of gram mole per atmosphere centimeter square second. So if you multiply it by partial pressure, it's gonna be gram mole per centimeter square second. Here it's mole fraction, so it's dimensionless. So this has the same units as Na, so it's gram mole per centimeter square second. And here I have Kc, which has units of centimeter per second. And here K, we give it the symbol of Kc to differentiate it from Kl. So Kc is the mass transfer coefficient in the gas phase, where the gas concentration is represented as molar concentration, but this is Kl is the liquid phase mass transfer coefficient. And what we did here is valid here as well. So we can get the relation between Kg, Ky, and Kc. So Kg multiplied by Pa minus P interface, and the flux equal Ky multiplied by Y minus Y interface. Y is, according to Dalton's law, if it's an ideal gas, we can say that it's partial pressure divided by total pressure. So we can put it as Ky divided by P multiplied by the same bracket here. The same for the concentration. If it's an ideal gas, then C equals P over RT, so I can put the equation in this form, and we can easily tell from this that Kg equals Ky divided by P equals Kc divided by RT. So this is how we can get the relation between the mass transfer coefficient in each of the two phases and convert from one to the other. This is pretty important, because in many cases you don't have the units that are homogeneous, or they are adjusted well before you start. You have to do some calculations to put the units in a form that is suitable for you to use. There is one last note here, which is a very, very important note, and I believe this is important because a lot of students get confused about it. Here we got the relation between the fluxes or between the mass transfer coefficients for liquid phase, and this is the relation between the mass transfer coefficients for the gas phase. It's not possible, and it's not logical, and it's not right to get a relation between this KL and this KG. There is definitely no relation. I cannot say, for instance, that this KC equals KX divided by CL. This is totally wrong. You are now calculating a mass transfer coefficient in a gas phase using another mass transfer coefficient for another phase, which is totally wrong. So these relations are valid for the gas phase mass transfer coefficients. So you are converting from a mass transfer coefficient to the other because this mass transfer coefficient is multiplied by the same driving force with different units. So it's the same driving force. It's mole fraction minus mole fraction. It's the driving force between the 2 points in the bulk of the gas and the interfacial concentration or mole fraction in the of the gas. These are the same as these, but with different units. These are the same as these with different units. It's okay to convert or get a relation between this K and this K and this K, because they all represent the same system. They all are multiplied by the same driving force with different units. There is no way you can get a relation between this K, this or this, and any K here. It's not right. So please keep this in mind. We have this relations based on the derivations that we have here. So you cannot get a relation between this, and each one of them is calculated based on the physical properties of the phase, based on the velocities, based on the flow properties, based on many things. So it's totally different in liquid phase from vapor phase. So I hope that this point is clear, because I see a lot of mistakes in this part. Okay, so this is all for this video. Next video we'll see how we can or talk more about the graphical representation, take it one more step further to describe the overall driving force and how we can represent it graphically. So I'll see you then, inshallah. Goodbye.